All right, everyone. Hello. We are live. Cool. So let's get started. My name is Niels Van Tielen. I'm the Chief ML Engineer at Union AI. Union AI is a startup that is basically building an end-to-end AI development platform, and you can, do everything from deploy agents to train models to building data sets that power those models. And today I'm going to talk about and give you a practical field guide to optimizing small language models, or SLMs, as I'll be referring to them, for domain-specific applications, domain-specific agents, that is. So maybe just to, I don't know who is here, but just to get the chat going, if folks are trickling in, maybe it'd be nice to just, if you have any questions throughout the webinar, feel free to throw them in the chat wherever you're beaming in from, either LinkedIn or YouTube. So yeah, happy to address any questions that come up at the end of the webinar. So let's get started. So a few weeks back, maybe 2 months ago now, NVIDIA published a position paper stating that small language models are the future of agentic AI. In this paper, they highlight a few key reasons, some counter-arguments, and barriers to adopting SLMs. And we'll touch on that a little later in this webinar. But one of the main motivating claims of this paper is that while language models are often thought of as these general purpose tools that can perform everything from open-ended dialogue to scientific research and more, actually in the context of agents, they're actually, they're used to carry out a small number of repetitive tasks with little variation. So just a little call out here for the Rick and Morty butter robot, whose only purpose is to pass the butter. And if you've ever built agents, this pattern actually where an agent is only responsible for, say, formatting unstructured text into some like JSON schema, predetermined JSON schema. And so they claim that because SLMs are already good enough at many of these repetitive tasks, they ought to be more widely used in agents. But even if we take this claim as true, the problem is that using SLMs in production actually doesn't come for free. Because SLMs tend to need more TLC in terms of fine-tuning to improve their performance on your specific domain, using SLMs takes us back to the operational complexity of ML engineering and ML ops, where you have to worry about all the things around model deployment, monitoring, maintenance, fine-tuning and training, and all the tooling and infrastructure that entails. And to make a chemistry analogy real quick, just like a catalyst can lower the activation energy of getting a reaction going, using the right tool chain and practices can drastically reduce the cost and effort you need to spend to enjoy the benefits of using SLMs in production, which usually lower cost overall. And so as you can see in this stylized graph, there's always going to be upfront investment, but if you use a legacy orchestrator or an orchestrator that's not purpose-built for AI, then the amount of cost and effort you'll have to spend on it is much higher. The maintenance after you've deployed the thing is much higher. Using resource-aware orchestrators that are purpose-built for AI can actually dramatically lower these costs and the effort to initially build and deploy, but then also afterwards reduce the ambient kind of cost and effort after deployment. And before we go on, I just want to be very clear in this webinar. This is about large language models versus small language models, not SaaS hosted versus self-hosted. To see the difference on the left side of this graphic, you can see on the left-hand side that you have SaaS hosted large language models through services like OpenAI or Anthropic or DeepSeek, etc. You can also have SaaS hosted SLMs with services like LibreChat and Hugging Chat, these are maybe less popular or less used in production, but they're there for you. In this webinar, I'm going to focus on the machine learning and AI teams who, for whatever reason, own their entire technology stack. So on the right side is the self-hosted side. And here I'm just highlighting, on LLMs and both LLMs and SLMs, there are options for kind of like the cloud host self-hosted and the local self. If you have a Mac Studio that can do inference on the largest DeepSeek model, that's sort of what I'm talking about. So if you're self-hosting SLM, it really means you're in a highly regulated industry like finance, or you maybe have strict data policies like the one, data policies that you might have if you're in biotech or health sciences industry. And also, just to note, local hosted, self-hosted SLMs could be a thing if you're kind of like a hobbyist LLM developer or AI developer. So this talk is for the ML and AI teams who need operational cost efficiency, sacrificing performance. And so for the rest of this talk, I'm going to unpack this SLMs of the future paper that I cited in the beginning. We'll get some definitions and the why, the barriers to SLMs. Then I'll walk through a journey to SLMs through a pain-driven development story, roughly based on conversations that I've had with people in the industry. Then I'll go into the meat of things, the incremental strategy to adopting SLMs. And I'll use a SQL agent case study here to kind of motivate things and make things a little bit more concrete. And then finally, throughout the SQL agent case study, how resource-aware AI orchestrators can get you fully operational with SLMs. So first, let's get some definitions out of the way. Again, I'm referencing this NVIDIA paper, so I think the definitions may vary, but they define an SLM as a language model that can fit onto a common consumer electronic device and perform inference with latency sufficiently low to be practical, so you're not waiting, minutes for a couple hundred tokens when serving the agentic requests of one user. And just to be clear about the complement of this set, LLMs are language models that are not SLMs, so they don't fit this characterization. To get to the why, I think it's important to note something that not many people know is that SLMs are actually quite powerful for some use cases already. They may need a little fine-tuning or prompt optimization that LLMs don't, but actually, if you played around with them, they're actually quite good at certain tasks. They are also more operationally suitable for agents, meaning that if you're self-hosting, again, I'm making that assumption, they're easier to deploy, they're easier to fine-tune, they're easier to work with, they're easier to debug locally. You can load them on your, M3, M2, M1, or whatever other laptop workstation you have. And then finally, they're more economical. So even when you put them into production, maybe you're using a cloud, GPU instance somewhere, it's going to take a lighter weight GPU instance for you to host the LLMs that power your agentic systems. So just to give you a sense of that last point, let's take a look at some of the hardware requirements and compare, let's say, a Qwen 3 235 billion mixture of experts model versus a Qwen 4 billion model. So if you assume a float 16 precision on the floating point representation for the weights of the model, the inference time memory requirements for the larger model is about 478 gigs, and the memory requirements for the smaller one is about 8 gigs. And if you look at the AWS and GCP instances that would be able to fit these at inference time, you can see roughly at face value, there's about 100x savings to be had using SLMs. Now, this is a very optimistic take on this, right? As I said earlier, SLMs don't come for free. Whereas LLMs may work for your use case right out of the box, SLMs do need a little bit more work to get them to be functional in your application. So I'll get into this. The highlights and barriers to adopting SLMs. This first point is the main one we'll be kind of focusing on in this webinar, which is large amounts of upfront investment that you need to get the model up and running on your own infrastructure, fine-tuning them, and then that goes all the way back to doing all the ML engineering stuff that maybe some of you are familiar with. The other 2 points are important too. So the second one is just around basically when you're shopping around for LLMs, right, or SLMs, you'll see a lot of generalist benchmarks being used to compare models. And this is kind of by design favoring large language models because by definition they are higher capacity. They just generally do better over a wider set of tasks. But actually, research has found that if you look at domain-specific benchmarks, say tool use benchmarks on specific domains, things like this, that SLMs can actually do way better or equivalently to LLMs. And finally, lack of popular awareness. People are aware that SLMs can actually do well on their applications, and hopefully this talk will kind of address some of this issue. So now let's talk through a pain-driven development story where in the x-axis you have time of the software, the agent project that you're building, and on the y-axis the operational cost and complexity of kind of running the thing, maintaining the thing over time. So at the beginning, you're generally the first user, right? You're building a proof of concept and you're asking the question, why does my application work at all? Or does my application work at all if I use this state-of-the-art LLM? The next phase would be something like an alpha release. So you may, give the agent to some of your coworkers to test it. And you may have something like 5 users. And you say to yourself, it works okay, but I need to start optimizing my prompts to improve performance. I might need an eval data set, something like this. Or just some basic observability around how my system is performing. And if you get past that phase, you'll do something like maybe a beta release where you launch your agent to some small limited set of users. You may get 100 users, and you're asking the question, now that we have some users, we should get some monitoring in place, make sure that the system is upholding some set of SLAs. And if you get lucky enough to get, say, 1,000, 10,000 users, in the general release, you're like, oh man, crap, we have much more users. Our cloud costs have skyrocketed. I'm using this LLM that I kind of deployed on my cloud, and there are latency spikes all over the place. My application is having to retry, and performance is degrading. So it's obviously stylized, but this is something that we've talked to people about in the industry in doing our own research in this space. And this is kind of the shape of sometimes what we see. Okay, so in the face of this, I'm going to now kind of talk about a high-level strategy to adopting SLMs. So I'm going to kind of assume you've built something already. Again, self-hosted LLM, maybe on like Azure or AWS or GCP, and now you've proven out the overall value of the application, and now you're in optimization mode. So you're trying to make the thing more cost-effective. So the first part is to identify key leverage points in your system that you can kind of swap out an LLM for an SLM call. The next part is you want to maintain performance. So how do you do this? You really want something like the equivalent of AI unit tests. Ideally with real data, but to begin with, you can start with synthetic data. Then you want to optimize experimentation speed, either experimentation on your prompt optimization technique or your actual fine-tuning technique where you're updating the weights of the model. Then you want to manage cost with heterogeneous compute. A lot of words there, so I'll kind of unpack that a little later. And then finally, optimize inference speed so that you're kind of maximizing or minimizing the latency or maximizing the throughput of your overall system. I'll take a quick break here just to take a look at the questions. I see here someone asked, I guess it's not either LLM or SLM. I have built AI applications using both by complementing each other to reduce latency and edge inferencing, while LLM still are the de facto scaler. Yeah, absolutely. I think these are kind of like what I was referring to in terms of the heterogeneous compute, or like the kind of mixed model here of using both in a single system. I won't like address that directly in this webinar, but I'll sort of hint at it, and hopefully you'll kind of see the answer to this question. But I guess it's more of a statement, which I do agree with. So again, to motivate this and to make this more concrete, let's talk about what a SQL agent might look like. This is super high level, right? But the architecture you might look at is your system will take in a user query, and you have an agent orchestrator here that's a language model call. And up front here, I'll just say agent orchestrators are doing a whole lot of heavy lifting. They're doing some planning. They're determining what tools to call. They're determining the terminal event, like whether or not it has the actual final answer to the query. So typically, this will remain the LLM in your system, right? But in the context of this, you'll have a bunch of different tool calls, and you may not call them linearly. There may be kind of loops that are not super deterministic in your system, and this is what the agent orchestrator really does. But these tool calls could be, if we just look at it linearly, right? The happy path case is you get a user query like, what was the conversion rate based on the data we have in our SQL database? Like, what was the conversion rate for the past 3 months of a certain set of users? So first, you want the agent to make a SQL CLI call to get sort of the metadata behind the relevant tables in your database. So you'll take that generated CLI command and do a lighter weight tool call here to get the table metadata. Based on that metadata, in your the agent's context now, it's going to maybe generate a SQL query, may go through a few loops of refinement of that query. It'll run that query, verify the answer, and finalize the answer to make it maybe more human readable. And then once the agent orchestrator figures out, okay, I have the right answer, it'll return the answer to the user. So this is, at a high level, how you might architect this kind of agent. To make, again, this a little bit more concrete, we're going to use Fly 2.0 as sort of our vehicle to show you what the code might look like for this, and what an orchestrator that supports these kinds of workloads might look like, and the kind of the properties you may want out of it. Whether you use Flight or you roll your own, or you're using a different type of orchestrator. But just for a little background, Flight 2.0 is a durable, fully dynamic, resource-aware AI orchestrator. And it solves a couple of problems that we've seen, right? So one problem is the need to learn a DSL for kind of workflow DAG orchestration. We've gotten rid of this. This is pure Python. There are limits to static execution, right? And the limits are really apparent when you're trying to build agents. And these are limits around conditional logic and loops and try exception handling, error exception handling. The third one is brittle pipelines. So these are pipelines where you have to like roll your own retry logic or start from scratch because you haven't cached intermediary outputs of tool calls and things like this, right? So that's something that Flight 2 handles really well. It's also difficult debugging things in production. So you have something running in production, and you can't exactly reproduce it locally because of some specific setup in your production system. And Flight allows you to sort of beam into like the production compute infrastructure that it is actually running these agents. The fifth problem is fanning out computation. So if you think about a deep research agent where it has to sort of come up with a bunch of hypotheses of what it needs to do web searches on, you will need to fan out these and test these different hypotheses, crawl a bunch of web pages or tools to make a bunch of tool calls to sort of build up your context to do the research. So Flight naturally handles this super Pythonically, just literally for loops to sort of do parallelized fan out. And the last part is that best practices are hard to implement, and so Flight does this kind of out of the box with containerization. Again, coming out with out of the box and more. So we'll unpack this. And what you get at the end is something that, as you can see here in this GIF, can make you a sandwich, at least a virtual one, where you can see the agent kind of making a plan for how to do this based on the tool calls of getting bread and peanut butter and jelly and assembling the sandwich. So that's what we'll be using, and we'll see this. I won't do a live demo, but we'll see how this with the SQL agent. So continuing on this case study, just to give you a sense of what this initial agent that I showed you, this one right here, where you have a agent orchestrator that's making a bunch of tool calls. It looks like this in Flight, right? So you define your compute environment at the top with your image and your dependencies. You define a task environment. This image will be used to run the functions below it, and they're just functions. We've defined our tools like over here, and the agent also is literally a function. This is pseudocode. You could use a framework like LangChain and Llama Index and things like this. But this is pseudocode to show you, again, you can implement this just in pure Python, where you have your agent loop that just kind of loops through steps at its disposal until it has a final answer. So if you recall the outline of this strategy, the first part is to identify key leverage points. So basically, you're asking the question, involve the simplest, most structured tasks, the things that you could probably delegate to a smaller, lower capacity model. And obviously, as I said earlier, you probably don't want to swap out this for an SLM. Maybe you can do it in some cases, but generally, based on what I've seen and what I've found, the tool calls are generally the place where you want to invest, swapping out LLMs for SLMs. And the kind of like the high level idea here is that the input space and the semantics of what you want the SLM to do or the language model to do is generally a little simpler when you consider kind of the things that we would say are tool calls, right? So these are things like creating SQL queries or refining the SQL queries based on natural language instruction. So just to make this a little concrete, you can sort of do this. This is a hand wavy analysis. You can do your own. But basically, the exercise is, you have a particular task, like a tool call or a particular thing that you want to do. And you kind of assess, like, what is its input space and what is its output space. And based on that, you can come up with a kind of a hand-wavy complexity score for each of these steps. And you can disagree with this. These are not. But so this is basically just illustrating, maybe I can start swapping SLM calls with this, step that creates a SQL CLI command to get the metadata, sort of the table schemas that are relevant to the query, right? So maybe that's something you tackle first. So this kind of gives you a little bit of a roadmap for what things you should try out first, and you'll kind of go through an iteration cycle, and then you might return to the other tasks on this table, and figure out what you want to swap out next. But say you want to start off with this first step. The first thing you want to do, actually, I mean, you could go ahead and swap it out immediately, right? But the thing I would first recommend, and this is, I guess, a good first step, and maybe to borrow like test-driven development, this would be a good first step for you to just establish a baseline with your full LLM system. So assuming all of your agent call or LLM calls are with the large language model, it's important first to generate some synthetic data for AI unit tests. So I'll walk through how this might look. So on the left-hand side, you have a SQL data warehouse where all your data is hosted. And you might build a pipeline that looks something like this, where you first get your historical SQL queries. You'll also get the SQL table schemas. And you'll then use an LLM to create synthetic user queries of saying, hey, based on these table schemas, what are some questions that you would want answered as a business analyst, for example? You'll get a bunch of queries and you'll run them on the actual data, and you'll get some table results, aggregated results back. And then you'll then do another language model call to create the finalized answers. And so you'll use these as basically your eval data set that contains the SQL queries, the synthetic user queries, table schemas, and then the answers generated by the LLMs. Right? And you'll then create an evaluation pipeline that takes your agent workflow, the one that we saw earlier, runs all of the eval data points on it, computes eval metrics, and then you get a kind of a report for the performance of your system. Right? I won't get into all the different eval metrics you could use here, but those themselves could be like the traditional NLP metrics, like Blue Score and things like that, or the LLM generated ones, things like roundedness and relevance and accuracy. And the code of this might look like this, right? And so the one thing I want to highlight is that, like, I'm using Flight here, so I'm using the same platform to both build my agent and build the underlying data and model infrastructure underneath it to kind of power the agent itself. So here again, I'm using environments, and I'm using different ones, right? So I'm sort of, something that I'll get to later in this webinar is that you can kind of disaggregate your compute so that you can use GPUs in one environment and CPUs in another. And really, this is just our data synthesis pipeline showed you pictorially in the previous slide. Okay, so these AI unit tests serve as your your test bed or your baseline for, okay, what is the performance of my agentic system? Later, you may gather some real eval data set based on real usage, but you kind of get it's kind of the similar idea. The next thing you want to do is optimize experimentation speed. Here, I want to highlight the fact that SLMs may need a little bit more work to get them to perform well on your particular agent application. So what I'm showing here is we're using the eval dataset we created in the previous step, and we're running the eval pipeline on a bunch of different prompts. And so you may start off with a seed prompt here. And again, we're relying on LLMs throughout and creating a bunch of candidate prompts based on the seed prompt. And you're basically asking the question, I want to evaluate all these prompts on the synthetic eval, and then I'll have some way based on the performance metrics, assuming that I can sort of reduce them into kind of a scalar value to select the best prompt. And one thing I want to highlight here is around the durability and recoverability piece of an orchestrator that you would ideally be using with this cached icon here, which means that if I run this pipeline and say I'm testing, I'm testing, let me go full screen again. Cool. I'm testing like hundreds or thousands of prompts. If my pipeline fails for whatever reason, maybe it's you're using spot instances or something like that, or you have some kind of system level error, that you don't lose your work and you're not wasting tokens and compute on prompts that you've already completed the evaluation for. So caching will come up again later, but just wanted to call that out as a property that you would either want to roll your own on your own, or select based on the orchestrator that you're using. And just to show you what the code might look like for this, right? In Flight, it's literally a keyword argument in the task decorator. And it's gonna automatically cache the eval pipeline based on the input, right? And talking about the fan out piece that I mentioned earlier, fanning out, and basically you're producing a bunch of candidate prompts at this step. And I'm just doing a for loop over the candidate prompts and using the Python's async IO to gather those results and therefore like run all of these in parallel. And the final step, obviously, is to select the best prompt. The experimentation speed also applies to when you're fine tuning. And so just one caveat here is I would highly recommend using prompt optimization first and exhausting that to get the best performance. Just because fine tuning is a whole nother can of worms, right? So you're actually updating the weights of the model, and you'll need kind of deeper ML expertise on plotting out loss curves and debugging loss curves and debugging. Let's say you're using PyTorch, debugging that whole stack to doing memory profiling and all these other considerations to effectively fine-tune a model. But assuming that you do have the expertise and you want to go lower down the stack, the same kind of concepts apply here. So you're still taking your eval data set, and you are preparing a fine-tuning data set based on it. You create n number of hyperparameters, and you are basically fine-tuning your model on your eval data set. You may have a holdout section of that data to compute test loss and test set performance and things like this. But the same idea, you select the best hyperparameters based on hyperparameter optimization run, and then that's the model you would use. Note that you would probably do both prompt and fine-tuning optimization. They're not mutually exclusive. And then managing cost. So I made a point earlier about leveraging heterogeneous compute. This is something that's super important if you want to squeeze even more cost efficiency out of your system. And so let's just take an example where you're using 3 sizes of model, right? So in this case, I'm using Quen 32 billion on the agent orchestrator, something a little bigger. Maybe I might use the 70 billion one. And here you may need 2 GPUs with 48 gigs of VRAM. Then, sorry, I keep coming out of presenter mode here. Cool. And then for some of my steps, I may be using the Quen 4 billion parameter model. And then for others, I may be using the 8 billion parameter model. I would recommend using 3 different models right at the outset, but let's just assume that this is kind of like what the optimal setup ended up being. You can actually, with Flight or with an orchestrator of your choice, one thing you ideally want is a way to provision different GPUs for the different needs of your small language models and your large language models in your system, right? So this is something that Flight allows for out of the box. So you would basically create a different task environment for each of the different workloads model. So you would have one for the Quen 32 billion one. So you'd have different requirements for the 8 billion one. And then for your tool calls, which may just be, may have the SQL client installed in it to just do those queries, you'll just need a super lightweight one, for example. And the final step in this overall strategy is optimizing inference speed. So to squeeze the most juice out of your system. And so we have this disaggregated compute. We have 3 different language models being hosted in different containers. What if you could reuse those containers over time, right? So instead of having a container per step for each step in the set of tools or set of that the agent is making, there's actually a way, there's ideally, and there's a way for this to do this in Flight, ideally you would want a single container per task type, let's call it, or workload type. And this is enabled through what Flight calls reusable containers. So in your task environment, you would basically have a reuse policy. And so again, just want to emphasize, this is sort of the Flight SDK. But the bigger lesson here is that in our platform, some affordance for you to declare a way, express a way for you to reuse the containers that you're using to load the model and then perform inference on it. And so the last image before going into sort of like the summary and takeaways is I kind of want to unearth this meme from kind of like the previous generation of AI or ML, as it used to be called, which is this paper, I think, called The Hidden Technical Debt in Machine Learning Systems. And this paper really was around machine learning, right? So this was like computer vision and I guess like the previous generation of natural language processing models and others, right? Is that actually just kind of like a small part of the overall production system of your machine learning system, right? You have all these other considerations that you need to keep in mind, like overall configuration, data collection, feature extraction, data verification or validation, the machines and the management of them, analysis tools for you to debug, managing your process, serving infrastructure and monitoring. And I think that the story here is that actually not much has changed. I mean, many things have changed, but in terms of this diagram, if you consider agentic systems, you have your agent code, right? You've built using a framework or building your agent from scratch. But when you're deploying these things into production, you may not have feature extraction anymore, but you may have something like context implementation or the assets you would need, like a vector database or sort of MCP service that your agent uses to augment its context. And the story is the same. The agent code is a relatively small part of the production system. You have all these other parts around it. And what I think is super important in production and something we think about a lot at Union when we're building Flight out is how do we best unify all of these subsystems in your overall agentic system. And there's a lot of hidden technical debt when you sort of start off just deploying your agent code and you don't have any of these other systems in place. And so with that, I want to just summarize sort of what I've talked about and what you've learned in this webinar. The point is that on paper, SLMs really should be more cost effective than state-of-the-art LLMs and perform equivalently, if not better, on certain domain specific, as long as you do some prompt optimization and fine-tuning. But again, this prompt optimization and fine-tuning may not come for free, or it does not come for free. You need to invest time in the right infrastructure, tooling, and practices and processes that enable you to effectively use SLMs. The overall strategy here is assuming you've gotten to a valuable agent application. So there's glossing over or assuming away the whole prototyping process of figuring out the applications that actually provide value for your business or organization. The overall strategy now to sort of make these systems more cost effective using SLMs is to first identify key leverage points. What are the points where all the LLM calls in your agent call, and where might you be able to swap out an LLM call for an SLM call? And I showed you one approach. There are probably many approaches, but a lot of it has to do with effectively how repetitive is the task, how much variability is there in what you're asking that LLM to do at that particular point in at the agent flow, and what is the nature of the task? Is it super hard and high level and abstract, or is it fairly concrete? Are you just like shuffling tokens around? Are you supposed to actually interpret and provide grounded meaning and accuracy to and interpretation to the tokens being sent into the input? Then, once you've identified these key leverage points, maintaining performance by building a synthetic data set to implement AI unit tests is important to set baseline, to catch regressions, things like this. Then you optimize experimentation speed because, as I said earlier, with prompt optimization and fine-tuning, there's a lot of iteration here that needs to happen. Managing costs by disaggregating compute. So you're using only the compute you need and not over provisioning based on the highest common factor of the largest LLM in your entire system. And optimizing inference speed by reusing containers, loading the model only once in the lifetime of an agent and reusing it as much as possible. And then finally, just sort of the properties you would want out of an AI native orchestrator, which is resource aware, so that it's not just running on a single Python VM or a single machine, but it actually is aware of, okay, this part of the workload requires these many GPUs, this other part only needs CPUs. So I'm maximally kind of using the compute provision per step in the workload. And we learned how Flight 2 actually enables you to do this quite easily just through literally Python. And with that, I want to end the webinar and just think. Last thing I'll leave you with is you can actually fly there right now. The link is there with the union.ai/beta. Any of the stuff you saw here, we are actively working with folks building agents on our platform, which is very cool to see. Here are just links to the docs and the launch video for Flight. And with that, thank you so much. I'll stick around for a few more minutes to answer any questions and address any comments.